Hello everyone, my name is Viraj and today we'll be looking at the fourth problem from the CP-31 sheet by TLE Eliminators under the 1000 rated questions. Let's go. So I'll move on to my sheet taking off 1000 and Olya and Game with arrays, fourth problem. Alright, Artem suggested a game to the girl Olya. There are a list of n arrays where the ith array consists mi, that is greater than equal to 2 positive integers. They will be called as a of i1, a of i2, so on till a of I mi. Olya can move at most 1 or possibly 0 integer from each array to another array. Note that integers can be moved from one array only once, but integers can be added to one array multiple times. And all the movements done are done at the same time. The beauty of the list of arrays is defined as sum of summation I equals to 1 to n, minimum of j equals to 1 mi, ai, aj. We will see what does that mean. In other words, for each array, we find the minimum value in it and sum up these values. The goal of the game is to maximize the beauty of the list of arrays, help Olya win the challenging game. Alright, so fairly simple problem. Let us see. They are saying that they will give you a number n. N will denote that you have n arrays. Every array is going to have a size greater than equal to 2. So let's take an example. Let's say I have 4 arrays. So I have an array A, I have an array B, I have an array C, I have an array D. Now in array A, let's say there are 5 numbers. So A1, A2, A3, A4, A5. Let's say B has B1, B2, B3. Let's say C has C1, C2, C3. Let's say D has D1, D2. So every array has greater than equal to 2 numbers. Now, what is given as an operation? You can basically pick up any number from a single array and move it to some other array. This can be done for one array only once. So let's say from array, maybe I pick up A3 and let's say I move it to C. Maybe I pick up B1 from here and I move it to D. Maybe I pick up C2 from here and move it to A. It doesn't matter. I pick up a number from any array if I want to. It's not necessary I do, but if I pick up only one number from an array and move it anywhere else. I do this for all the arrays. As in, I make my decision for A, whether I'm moving or not, for B, for C, for D, everything is done at the same time. When all this, you can say shuffling is done and dusted, I am trying to find the value that is, let's say V, which is actually equal to sum of all minimums of the array. Minimums of the array. Alright. As in, if let's say in this array, the minimum is A3, let's say this array B1, let's say this array C2, let's say this array D2. Then A3, B1, C2, D2 summation is actually this value V, which I want to print. Now, remember, this whole shuffling can be done anyhow. You can create so many different V values. That is why they are saying that using this operation smartly, what is the largest sum of all minimums of each array that you can make using this operation cleverly and print that answer. Alright, so I hope the problem is clear. Let us take a quick example. Let's take the last example. You have been given 3 arrays. Every array's size is given and then that array is given. So first array is like 4 size, then the numbers are 1001, 7007, 5 and so on. So I'll write this down. Basically, there's an array A that has the numbers 1001, 7, 1007 and 5. And of course is 3. Okay, let's create the second array. Second array looks something like this. You have 8, 11 and 6. 8, 11 and 6 and then array C, the third array, let's say looks like 2 and 9. Now what I can do over here is actually let us move this 6 to array A. Let us move this 2 value also to array A. So I basically end up with something that looks like this. 6 is not there anymore in this, 2 is not there anymore in this, and these 2 elements can be written over here. This is 2 and this is 6. Now in the first array, what is the minimum? 2. In the second array, minimum 8. In the third array, minimum is 9. Add it up, you actually get 2 plus 8, that is 10, 10 plus 9, that is 19. Check over here with the output. Yes, 19 definitely works out. Alright, so I hope the test case has now become clear. I did movements. I did movement from array B, I did movement in array C, and I made it go to array A. And from array A, I did no movement because again, as I told you, it's not necessary that you make a movement from an array. It's not necessary that you actually pick up some element and make it go anywhere else. The array A I kept as it is. B array's element I shifted and C array's element I shifted and I made best answer, that is 19. Alright, so I think you can pause the video now and give this problem one try of your own. If not, let's actually begin with the solution. So first of all, we need the expected time complexity that is there in this problem. One test allows me 1 second, that is 10 raised to 8 operations. And every test has this T, that is test cases, that is 25,000 that is given over here. But it is written that sum of MI over all test cases do not exceed 50,000. Now this tells me that I don't need to worry even about T, even about this N, because M is actually the main limit that is going to get expanded. So I can compare this M value with this T that is given to me. I can say that if one test basically allows me 10 raised to 8 operations, then M being over here in something like 50,000, I can actually create an O of M solution also. Even a little larger, something like M log M, this is also going to work. Even if I go something like M square root of M, that is also fine, but I cannot run something that is M square, because M square would be something like 50,000 square that crosses 10 power 8 boundary. So this is something that is not expected, and solutions like this are good to go. So anything in linear to M up till, of course, if you go down to constant, all of this is good to go. And this is my expected time complexity, which is now very, very important, because by this I have a clarity that what sort of a solution can I actually make. Great. Let us begin with the idea and the problem. So let's first take a general case. I took array A, let's say A1, A2, A3, A4 and so on. Let's say the array B, B1, B2, B3, B4 and so on. Let's say array C, C1, C2, C3, C4 and so on. And let's say array D, you have D1, D2, D3, D4 and so on. Now just for simplicity purpose, let me make sure that these arrays are sorted. Why? Because I am going to work with minimums only. So it is better that if I sort them, because then diagrammatically, I would only want to work with the first elements then, right? So I have imagined that made sure that A1 is less than equal to A2 is less than equal to A3 is less than equal to A4. Similarly, B1 is less than equal to B2 and so on. Similarly over here, similarly over here. So all these are sorted. Now, right now, if these arrays are sorted, what is the V's value? The current V value actually is A1 plus B1 plus C1 plus D1. Very simple. That is basically the sum of the first values that come in the array, because everything is sorted individually, every array is sorted. So the first values are the minimum values. But now you have the availability to do an operation. Remember, greedily, you want that this value V increases. Now the only possibility that this value V increases is somehow if these four elements increase. If this happens, then automatically the V value will go up because the summation values have gone up. So if I talk about array A, tell me in array A, right now the element that you're considering is A1. If you don't want to consider A1, then what do you want to do in array A? Don't you think that you will have to move this number A1 from array A to somewhere else? Because right now this array A's minimum is A1. So you know that if this array's minimum has to change, the minimum right now has to go away. And if that happens, tell me, which is the new minimum now? If A1 is removed from array A, and let's say it goes somewhere else, where does it go? We'll of course discuss. But let's say A1 goes at some place else, then A2 becomes the guy which is now the new minimum of the array. So A2 is the second minimum, now becomes the first minimum. Similarly, from the array B, if B1 is made to go away, then B2 will become the second minimum. If C's array C1 is made to go away, then C2 becomes the minimum. D1 gone, D2 becomes the minimum. So the answer can actually change from A1, B1, C1, D1 to rather A2 plus B2 plus C2 plus D2. That is a possibility. But the idea is we haven't actually clarified where do we actually make our previous minimums move to. Where does A1 go? Where does B1 go? Where does C1 go? Where does D1 go? Listen to this very carefully. It would be ideal to put all the first minimums of all the arrays right now into some array that we can call as dumping array. And that dumping array should be actually the array which has the lowest second minimum. Let's write this argument. Argument is we would ideally want to dump all the first minimums to an array which has the lowest second minimum. What does this mean? Let's say that in this array right now, A2 is the second minimum, B2 is the second minimum, C2 is the second minimum, D2 is the second minimum. Let's actually place some values there for placeholders. Let's say A2 was 3, B2 was let's say 4, C2 was let's say 6, and let's say D2 was 1. Now, if I move all the elements, that is A1, B1, C1 and D1 to the array D, then what will happen is 3 will become the new minimum, 4 will become the new minimum, and 6 will become the new minimum. And 1 will not contribute anymore, which is fine because out of these 4 values, 1 was the smallest. Now think this greedily. If you would have dumped these 4 values into some other array, let's say you would have dumped these 4 values into the array C, then 6 would not have been the new minimum of the array C. And in that case, you're losing more. Right now, you're only losing 1, but then you will lose 6. And your overall V value will go even lower, which is better. Do I want to contribute a 6 at this location, or do I want to contribute a 1 at this location? Of course a 6, right? Because it makes my answer go even higher. So don't you think it is smart and greedy to actually choose the array which has the second lowest minimum and make that the dumping array? Move all the first minimums to that particular array, which is by the way possible also, because if you read in the question, it's very clearly written that integers can be added to one array multiple times. So I'll pick up all the first minimums and I'll shift that to the dumping array. Dumping array would be the array which has the lowest second minimum, and then automatically the arrays which were not the dumping array, their second minimums will become the first minimums, as in this case, A2 becomes the first minimum of A, B2 becomes the first minimum of A, C2 becomes the first minimum of A, and then imagine that all of these elements, let's remove them from here, all of these elements have moved over here. This is A1, this is B1, and this is C1. And now in this array, whichever is the minimum element, after I have dumped everything, that is the number that pops from here. It might be A1, it might be B1, it might be C1, we don't know. We can of course keep a track of that. Or it might be even D1 also. We don't know, we can keep a track of that. Alright, so our answer would now become that A1 has changed to A2, B1 changes to B2, C1 changes to C2, and D1, this number D1 overall, changes to some other number which is actually the minimum in this array. Maybe that number is M, so this becomes M. And by this idea, you have greedily made sure that you actually increase your value V by a very high margin. To be specific, this is drastically the highest value. And this is the greedy idea. Pause the video, I'll repeat the idea once more. I will try to create a dumping array where all the first minimums will be shifted. That will greedily help me in creating the arrays which are not the dumping ones to have their first minimum go away and their second minimum become the first minimum. And the dumping array will be selected by me greedily, which has the lowest second minimum, so that I know I am not choosing an array whose second minimum was very high. I am choosing the array which second minimum was so low that its contribution can be neglected and it can be created the dumping array. As explained in this case, it was better to make D as the dumping array, considering, for example, D2 was 1, because D2 was the lowest in all these second minimums. Choosing D as the dumping array was the smarter move. Alright, I hope this makes sense. Let's do something. Let's actually run our idea on the third test case once more and see, does this check out? So we had the numbers that looks like this. You have 0, 0, 1, 7, 1, 0, 0, 7, and then 5. Then you had 8, 11, 6, 8, 11, 6, and then you had 2 and 9. So as for simplicity purpose, we said that we can sort the array so that it's easier to identify the seconds and the first minimums. So let's do that. Let's sort this array quickly. So the above array would actually look something like this. 5, 7, 1, 0, 0, 1, and then 1, 0, 0, 7. And the second array looks like 6, 8, and 11. And the third array is 5. Now in this, what is the first minimums? 5, 6, and 2. Now I want them to go away. So which array should become the dumping array? Which has the lowest second minimum? Let's see. The second minimums are 7, 8, and 9. So which is the lowest second minimum? 7. That means the array A should be considered, or the first array should be considered as the dumping array. So now I'll move this 6 and you can say 2 over here. And then after this, this is array A, this is array B, this is array C. So B's and C's new minimums are the second minimums now. So that is 8 and 9. And A's minimum now is, out of all such values that are inserted, dumped, and the previous values, everything combined, the new minimum is actually 2. So 2 plus 8 plus 9 actually lands me 19. And this is why my idea checks out. Alright, now you can pause the video and see for yourself that had you actually chosen B or C as the dumping array, your answer would have not worked. Let's see. If I go back and back and back, right till here, and let's say I would have chosen, for example, let's say I would have chosen B array as the dumping array. Now in this case, 5 would have moved at this location, 2 would have moved at this location. Now the value would have been 7, 9, and 2. Add this 7 plus 9 plus 2. Do this mentally. This is 18. 18 is not exactly the highest value. We just saw that we can make 19 as an answer. So why would we want to go with 18? Not feasible, right? That means our idea is checking out. The greedy thing of taking the dumping array to have the lowest second minimum actually works. And this is the whole problem. All right, now let us move to implementation. I hope this part should be clear. Make some more cases of your own, and I think this should, of course, be very, very clear to picture. Now, how do we implement this out? We can, of course, try to simulate this dumping thing that I told you right now, but it's no need because we can actually figure out our answers very, very quickly by just doing a very smart mathematical calculation. Let's say there are 4 arrays and they had these elements A1, A2, A3, so on. Then B1, B2, B3, so on. Then let's say C1, C2, C3, so on. Then let's say D1, D2, D3, and so on. Now in this case, for example, let's say that array D had the D2 value to be the lowest second minimum. Then what was the answer? I'll mark this off. The red box, of course, A2, B2, C2. And then if you think this very cleverly, actually in the array D, after you dump all these 3 values, or rather these 4 values, although D1 is there only, so it doesn't matter. But when you actually dump these values in array D, the new minimum of the array is not going to come from all the other elements that were there in the array. Actually, the new minimum in the array will be the minimum out of A1, B1, C1, and D1 only. Which means that the answer actually is going to be this red box plus, let's say this is the yellow box of all the first minimums. And in that, whichever is the lowest amongst this, let's say call that M, this is actually the answer. That means sum of values in red box plus, you can say, M, that is the lowest first minimums, is actually the answer. So to calculate this, I can calculate this red box. To go one step even further, I can write it even more like this. It would be very hard for me to calculate this D2 value because in this example, I knew D2 was, for example, the lowest second minimum. But to be very smart, what I can do is I can store all second minimums. Okay, I can store all second minimums and then I can sort this vector. Now, if I sort this vector, this will have all the values that are the second minimum, basically all the values in this second column. And from now on, what I can do is I can take sum of this vector, and from that I can remove the first value in the vector, that is V0. This is actually equivalent to writing the sum of the red box, because the sum of the red box was the sum of all the second minimums minus the lowest second minimum. And on this answer, on top of this, I can write plus lowest first minimum. Now for this lowest first minimum, I don't need any array. As I would be taking input, I will make sure that if I'm starting at the first element, I know that I can keep some variable M, let's say, or whatever you call that. We will see in the code part and minimize that variable with all the first hand values. And this is the whole answer. So writing this once more, it turns out to be something like this. M plus K minus S, where M is the lowest first minimum. K is the sum of all second minimums, and S is the lowest second minimum. All right. I hope this is clear. If I go back in the main case also, the third case that we were discussing, over there also this would have worked out. Why? Because your array was initially something like this. You had a 5 over here, you had a 2 over here. So if you'd have taken the lowest in all these 3 values, that is 2. The sum of all these values, that is actually 7 plus 8 plus 9, and minus the lowest in this value, that is 7. So you would have written something like this: 7 plus 8 plus 9 minus 7 plus 2. This would have actually turned out as 90. So let us move on to coding now and see this in motion. We have t variable, we take the n, then we have the vector, second elements, I'll call this, then the lowest first minimum, initially int max. Let's run a for loop 0 to less than n. M is taken input and the vector of M size is taken input. I'll sort that vector because now I know I can work with the first value at A0, the second value at A1. A1, or the second minimum rather, is pushed in the second elements vector, and the lowest first minimum value is just minimized, or this variable is just minimized with A0 every time. So now when you come out of this whole structure, this second elements vector stores all the second elements in sorted manner of each vector. And this lowest first minimum is actually the lowest among all the first minimums in the vectors. Now I have the sort function on the second elements array, and then I can accumulate this out so that I get the sum. And then the first value of this second elements vector is actually the lowest second minimum. Now lowest first minimum plus sum minus lowest second minimum gets me the answer, and I can print it. This is going to be my main solution. Now, what is the time complexity? This can be a little tricky. See, this is going to run in n order, and then inside this, you have this m order of input, but inside this is like a m log m function more that is basically sorting this. Now, you might say that the time complexity turns out to be something like n into m log m, because I'm basically talking about a test case. But remember, we said that we are not going to worry with a test case since this m has a very nice limit of 50,000. Overall, every test case, if you just combine all the m's, they still don't cross 50,000 boundary. So I can directly compare this highest factor m over here, and that is going to be fine with me. So I can write that my time complexity turns out something like m log m order, which is going to work fine, right? This is going to be something like, if you pass 50,000 in this is going to have O of 50,000 into, you can say log base 2 of 50,000. And this is going to be something like 10 power 6 order, which is fine. And what about space complexity? Space complexity is again majorly dependent on m only, where m is O of 50,000, that is 10 power 5 order. So 10 power 6 is comparison to a test, which is 10 power 8. So this is fine. And space complexity is again comparison to a test, not a test case anymore, which is 10 power 5, which is also fine. So both things work out. I don't get a TLE. And this is my whole solution. All right. So very greedy idea. I hope this makes sense. That is all that is there in this video. I hope you like it. Thank you for watching.